Welcome everyone to yet another session. We wish to acknowledge this land on which the Face Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississauga of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. I welcome everyone to today's seminar with Dr. Folashade Agusto, who will give a talk on tick and fire, and we will be exploring the effect of prescribed fire on tick-borne disease. Dr. Agusto got a PhD in mathematics from the University of Ilorin in Nigeria, and she was a trained applied mathematician based in the Department of Ecology and Evolutionary Biology at the University of Kansas. Our work focuses on designing novel models to gain insight on the emergence and reemergence of infectious diseases of public importance and how to mitigate the risk they pose on human health. She has designed and analyzed novel models for diseases like Ebola, avian influenza, malaria, and so many others. And our current works are on modeling tick-borne disease across the Great Plains, and as well as understanding the role of human behavior on the transmission of COVID-19. Dr. Agusto, the floor is yours. Thank you.
Well, thank you, Jimmy, for the invite and the kind introduction. And thank you everyone for coming. So in this talk today, I will specifically be exploring the effect of prescribed fire on Lyme disease. So as overview to this talk, I will give a brief introduction about Lyme disease and some Lyme disease statistics. Then I will talk a little bit about prescribed fire. I will then introduce two impulsive models. One is spatially implicit, and we actually started this work with this spatially implicit model during the 2020 lockdown. And then I would present the other impulsive model, which is spatially explicit. I'll give some results of some scenarios that we ran, then I'll close with a summary. Tick-borne illnesses from both endemic and emerging tick-borne pathogens have shown dramatic increases in recent times, as you can see in this, one second, I'm trying to get the laser pointer. As you can see in this graph right here, and this represents an increasing public health risk in the United States. So for instance, Lyme disease had gone from 4 cases per 100,000 people in the 1990s to 10 cases per 100,000 people in early 2000s. So this risk continues to evolve as new pathogens are discovered. Now this chart shows the different tick-borne diseases and pathogens that have been discovered between 1960 and 2020. Now, overall, there are at least, till date, there are at least 18 established tick-borne infectious pathogens and diseases, from Rocky Mountain spotted fever to Lyme disease down to bovine virus. There are 20 known conditions like the Afo-Gal and 13 other tick-borne illnesses. Unfortunately, the tick species are expanding their geographical ranges, which are further exacerbating the risk of that tick pose to humans, this ticks pose to humans. And these are maps of the geographical ranges of 2 Exodus species, Exodus scapularis and Exodus pacificus in 1996 and in 2020. And you can see particularly in the eastern parts of the United States, the expansion that these species have done. And these 2 particular species are competent vectors for transmitting Lyme disease. Now this expansion of course is not limited to the Exodus species. The map on the left shows the current location of where you would find Amblyomma americanum, while the map on the right shows the future prediction of their expansion. And you can see this expansion towards the northeastern parts of the country. Now, ticks have complicated life cycle. Like can span from 2 to 3 years, depending on the tick species that we're considering. And they have 4 life stages. So we have the eggs, the larvae, the nymphs, and the adults. And so here are the male and the female adult ticks. So the eggs are usually laid in spring, and then they mature into larvae in summer. And then this newly emerged larvae require blood meal from a variety of hosts, from birds all the way to small mammals like mice. Then once fed, they would then mature into nymph the following year, the spring of the following year. So this newly emerged nymph also require further blood meal from this variety of hosts. So once fed, they would then mature into adults in fall of that first year. And then the matured adults will feed on this variety of mammals. They prefer larger mammals in this case. And then once fed, they then lay their eggs in the second year, the spring of the second year. Now, Borrelia burgdorferi, which bacteria is responsible for causing Lyme disease, and this is mainly present in the black-legged ticks. So these ticks are black-legged ticks, and these are especially present in the nymphal stage of their life cycle. And ticks are really small, as you can see in this reference of the ticks to a dime. That's how small that they are. And the nymphs constitute the most risk of getting the Lyme disease in humans. Now, according to the CDC, Lyme disease is the most common vector-borne disease in the US, and I was particularly surprised at these statistics. I was expecting it to be mosquitoes, but it's Lyme disease. And there are about 40,000 cases reported each year in the United States. However, the true prevalence of the disease might be closer to 450,000 cases per year. So Lyme disease symptoms are diverse and they can be very devastating. Many people with early stage Lyme disease develop a bullseye-like rash, circular rash at the site of the tick bite, which usually appear between 2 to 30 days after being bitten. And some of those early symptoms include chills, fever, and headache. And there can be other complications from the disease, like short-term. There's something in the chat. Am I supposed to read this now? Is that a question?
Also, we can ask a question after we are done.
After, no, I just put things in the chat for people to.
Yeah, don't worry, we'll ask the question after. Okay.
Okay.
Yes.
All right. So we have complications from severe Lyme disease, and this includes short-term memory loss, and we can also have neurological problems like meningitis, nerve inflammation, heart problems, facial nerve inflammation like the Bell palsy, or joint swelling, which could involve the knee or the elbow. So far I've been talking about Lyme disease, so I'm going to switch gear and talk a little bit about prescribed fire. So prescribed burns are intentional fire necessary for land and forest management, farming, peril restoration, and greenhouse gas abatement. And control fires are particularly appealing due to their time and cost efficiency, along with their ability to be applied across large amounts of land. And they are particularly effective in controlling tick populations because it kills off the ticks and destroys their leaf litter habitats. And and they generally happen in late spring and early summer. And this time happens to coincide with when we have the most names questing for ticks, questing for hosts. So this map is a historical map of the mean fire interval. And this is prior to the industrial influences and long before we have increasing land use and historical fire frequency map. On the right, both the current and the predicted geographical ranges of Amblyomma americanum, we'll see these two lines. The black line corresponds to their current location, and the gray lines are where they are predicted to expand to. And you can see that the expansion is towards the parts where we have lesser fire frequency. Of course, there are other factors that are responsible for this. So it's not just the fact that we have fewer fire burning in this particular region. So factors like climate change and bird migration. Now, while in this presentation, I am talking about tick-borne disease that is important to the US. Ticks are found worldwide, and so is the occurrence of prescribed fire and fire incidences. So for instance, this is the map of the average annual fire burns from 1960 to 2000. Regions with lighter color have lesser burnt area, while regions with darker shades burn over 60% of their land area. So as far as ticks are concerned, they are also found globally. And this is Amblyomma iberium, which causes Rickettsia disease in Africa. And this is a map of the distribution of some pathogenic and unknown pathogenic Rickettsia disease across North and Sub-Saharan Africa. And Africa particularly is known as the fire continent, as we saw in that global map of the average annual area burns. Sub-Saharan Africa particularly burns over 60% of its area. And research on the effects of fire regime on the African ecosystem have been conducted since the early 20th century. And this has led to a general understanding of the effects of different types of fire and fire intensity, as well as the understanding of the seizing and frequency of burning of the grass and tree components of the vegetation. Now, to the study. So our goal in this study are twofold. So one, to show the effects of prescribed fire intensity and the duration between the burns on tick population and Lyme disease. And by intensity, we consider low and high fire intensity. And secondly, to consider the effectiveness of the burn on different spatial domains. So I'm going to start by considering the effects of low and high fire intensities, as well as the duration between the burns on the effectiveness of the disease. So because this is our first start into this, which we did during the lockdown program, so we started with this extremely simple model, really, really simple and especially inexplicit. So the red compartments are for small mammal hosts, while the blue compartment captures what happens within the ticks. And so the host population are further segmented according to their disease status. So we have susceptible and infected. And for the ticks, we also have susceptible and infected. And we further segmented the tick according to their life stages. So we have eggs, larvae, nymphs, and the adults. We don't have vertical transmission in this case. However, if a tick is infected at a particular life stage, they carry the infection on to the next life stage, as you can see over here. So with this, we have the following system of ordinary differential equation. And to capture the effects of fire, we use an impulsive system, where at time before fire, a system follows the system of ordinary differential equation that I showed, which I'm still showing. But when we applied fire, the tick population and the host population are reduced by a certain proportion, and that's captured by the system of equation. Now, to estimate the parameters capturing the two fire intensities, we use data from literature. However, we're currently in talks with some folks at our field station who are doing some fire experiments to collect tick data for us as well. So first, we used the data from PADCAD 2009 paper to estimate the parameters related to high fire intensity burn, and the paper by Gilliam et al. To estimate the low fire intensity related parameters. Now, the paper by PADCAD et al. Had fire data for 6 tick species and rodents, and we used the data for Exodus pacificus, which is a competent host to transmit competent vector to transmit Lyme disease, while the data for Gilliam et al. Data has fire data for 3 tick species, and we use the data for Exodus scapularis, which is another competent vector. However, the study by Gilliam didn't include any rodents, nor does he have any control. So to estimate the parameter quantifying the reduction in the tick population as a result of fire, we took the difference between the ticks in the control and the burn sites, and we normalized it by the total tick population. I know that some of you will be expecting me to show you some mathematical analysis. I don't have that in this talk. Some of the results of this work is publicly available, so you can check that out for some of the analysis that we did in that study. So we simulated the model using data from literature with the other model parameters and the ones that we have been able to estimate from the fire study. And so here, this result here is showing us the effect of the 2 fire intensities that we carried out. On the x-axis that we have time, on the y-axis we have the infectious means population, and we're particularly focusing on the infectious means population since they pose the most risk to humans. The pink curve corresponds to low fire intensity, and the dashed blue line corresponds to high fire intensity. And we, of course, carried out the simulation for a period of 6 years. So while we have the same number of tick prior to the implementation of fire in the first year, you can begin to see the difference between the 2 kinds of fire that we have. The high intensity fire seems to be more effective in controlling the population of ticks, as we have fewer number of ticks in this case. So next, we consider the effect of the duration between the burns. On the left, we have the results from the low fire intensity. On the right, we have the results of high fire intensity. And again, we're still focusing on the infectious means population. We burn 1 time every year for a period of 6 years, once every 2 years for a period of 6 years, once every 3 years for a period of 6 years, and 1 time in 6 years. And you can see that low intensity tend to have tend to be less effective compared to high intensity, just as we saw previously. And the burn effectiveness increases as the duration between the burn increases. So for instance, if we burn every 2 years at low intensity, that we have fewer number of ticks compared to when we burn every 2 years at high intensity. So this is focusing on this, the yellow or the gold color bar. And also if we burn every 2 years, we have fewer number of ticks compared to when we burn every 3 years. And this is regardless of whether we're doing low intensity burn or high intensity burn. So overall, intensity has a larger influence on the tick reduction than the duration of the burn. And we see that it's better for us to burn fewer times at higher intensity than to burn more often at low intensity. So I've been considering the effect of low and high fire intensity, as well as the duration between the burns on the prevalence of the disease. So now I'm going to switch gear and talk about the effectiveness of the burn on different spatial domains. So we extended the model by adding spatial dependency. So for instance, these are the variables for the host population. So it does not just depend on time, it also depends on the X and Y coordinates, spatial coordinates. We equally added diffusion term to some of the model population in order for us to be able to capture the dispersal of the population across space. And our solutions are considered in two-dimensional rectangular domain omega. So this is the model with the spatial dependency, which we have suppressed here for compactness sake. And here are the diffusion that we added to the model. Now the juvenile tick population have the same diffusion rates as the small mammal host, while the adults has the diffusion rates akin to the deer population, which they have affinity to preference, which they preferentially feed upon. And we didn't include the deer population in this model since they're not competent hosts in this case. And this, of course, is subject to the impulsive prescribed fire conditions. And a reaction diffusion system is then coupled to a homogeneous Newman boundary condition. So in our model, we use constant diffusion to model uniform dispersal of the population across space. Later on, we would relax this condition where we consider heterogeneous domain. So to solve this impulsive PDE, we use a mesh movement and finite elements package written in MATLAB. This package was developed by my colleague and collaborator, Professor Wai-Jean Hong. So it's a finite, so this finite elements method splits our domain into a spatial domain into smaller, easier to solve subdomain or elements. We then calculate our solutions over each of these smaller elements and then add them all up to get a full solution at the point, at one point in time. And we use the implicit fifth order Radal 2A method in time with variable time step. So next, I will present some results of some scenarios that we ran where we assume that ticks and Lyme disease are already endemic in the area. So as with the ODE system, we simulated the impulsive PDE using data from literature and the estimated reduction in the tick population, both the tick and host population as higher. So in this first scenario, ticks are distributed evenly across a homogeneous domain omega. And omega is a 30 by 30 square block where prescribed fire occur in a 10 by 10 block in the middle of the domain. And you can see this immediate reduction in the number of ticks at time T1. At time T2, T3, you can begin to see the effect of diffusion of the ticks back into the bond patch. And at T3, this becomes noticeable. And over time, the number of ticks in the bond patch and the surrounding area of the bond patch is lower compared to what we have at the edge of a domain. So as with the ODE system, we see a reduction in the percentage number of ticks with increasing number of burn. And this reduction also increases with the patch size of the bond area. However, we see a diminishing return as the size of the patch increases. And this can be attributed in part to the effect of diffusion and the speed of tick recovery back into these bond patches. So next, we explore the effects of prescribed fire in a heterogeneous domain, which captures the different environments that ticks can be found. And we split a 30 by 30 square domain into two non-uniform domains. The first domain, which represents a grassland, so that's this X less than 15. is not as suitable for ticks because it generally has a higher temperature and low humidity. And so in that particular domain, we set our diffusion rates low. And in the second part of the domain where X is greater than 15, this represents a wooded advantageous environment where ticks have higher diffusion rates with plenty of leaf litter and space to hide when the temperature increases or humidity drops. And we burn 10 by 10 block on opposite corner of the domain. So this is what we have at T equals to 1. At T equals to 3 and 5, you can begin to see the difference between the two environments. And at the end of our simulation period, which in this case is 10, you can see that we were able to reduce the tick population in the wooded area compared to the non-advantageous environment for ticks. And persistently, if we continue to apply prescribed burn, we achieve more reduction in that part that is suitable for ticks compared to the parts that is not suitable for ticks where diffusion rate is lower. So lastly, we explore the effects of prescribed burns on the invasion of ticks into new area. And we introduce into this 10 by 10 square block in the corner of the domain ticks, and you can begin to see a traveling waveform as the tick as the tick propagates across the domain if left uncontrolled. And this become obvious at the end of a 20-year simulation. So in this particular scenario that I'm showing you, there's no prescribed burn. So the ticks are just let loose. You can see how much the tick has propagated and how much they have grown. However, if we apply prescribed burn, say every 5 years for a period of 20 years in this patch of introduction, so this 10 by 10 block where we first noticed them, you can see a disruption in the traveling wave. However, the invasion fronts of the ticks remain the same. So this is when they are uncontrolled or undisturbed. And this is when we just apply the burn every 5 years. So the invasion front pretty much is the same. However, if we say we apply prescribed burn every year for a period of 20 years in that patch of introduction, we are able to slow the invasion fronts of the ticks, but nevertheless, the tick have already escaped that patch of introduction. And so with that, we have another question. So this makes it obvious that prescribed burn cannot just control it. So it's not with prescribed burn, we cannot control the tick population. So we need to, in addition to prescribed burn, pair this with other kinds of control. And so that begs another question: where should we place this other control? Should we place them in this 10 by 10 block, or should we place them at the front of the invasion front? And so this is some of the new questions that we are beginning to explore as far as this research is concerned. So in conclusion, I have presented two impulsive systems, one implicit and the other explicit in space, in order to be able to determine the effect of fire intensity on disease prevalence. And we saw that generally burning at high intensity is preferable to burning at low intensity, and we should be able to do this whenever possible. Although high intensity burn might not be realistic due to environmental factors. And we also saw that location of the prescribed burn can be crucial in determining its effectiveness. And burning in an environment that is suitable for ticks, like the wooded area, can lead to fewer number of ticks, unlike burning in the grasslands that are not suitable due to the fact that we have high temperature and low humidity. And then lastly, we saw that it may be better to implement other kinds of control in order to slow the propagation of the ticks into new environments, so as to prevent their establishment. So this work was done by my amazing team. So it got started during the 2020 lockdown with Emily Gao, who's an undergrad who lives in Lawrence. She's at the University of Washington in St. Louis. And my grad student, Alexander Falk, is continuing the work. And so he's the one doing the PD-related work. And this is Professor Wai-Jun Hong here at the Department of Math. And so he developed the finite element package that we use. So this work was supported by funds from NSF. Now, before I close, I'm going to shamelessly put in a plug to say that come join my lab. We have tons of questions that we want to address with this tick problem. And we do have a beautiful campus, as you can see. This is Sunrise on Jayhawk Boulevard. And I don't know if you guys have heard this about Kansas. Lawrence is not flat, our university is on the hill. And if you're a lover of snow, we do have snow. This is another aerial view of our campus. So thank you. I will take your questions.
Wow, thank you so much for the great presentation. And that was relaxing. Thank you. I have a few questions, but okay. I'm going to ask one and allow others before I ask more questions. So my first question is, so for example, from the bar plot, you had the low intensity and high intensity. Then okay, maybe we can go to the plot. Yeah, that one. Yes, this one. So this is low intensity and high intensity. Then it's based on the number of frequency of bonds, like per year or per 2 years, or once but in 2 years. So I'm just wondering that did you consider the land space? I mean, not in form of diffusion. For example, if we burn on like an acre of land and we burn on like 1,000 acres of land. So I'm thinking that burn, low intensity, may behave like a high intensity on a small amount of land or a small part of land. And the low intensity may behave like high intensity actually when the burn is occurring on a small part of. So did you consider the land space of the burn?
Thank you. Well, thank you very much. So for this particular result, this is for the spatial inexplicit. So there's no space in this one. For the one with space, we did look at the factors, the spatial domain, the size of the spatial domain, but we didn't consider it in terms of high and low intensity. We just mainly focused on the high intensity since that seems to be more effective than controlling, than using low intensity. So this is the one that we had here, but that's a good question that we didn't consider. Here we were increasing the patch size and seeing the percentage number of ticks that are remaining.
So the patch size is the land size or the population of the ticks?
No, the patch size is the patch of where we're burning.
Oh,
okay. Yeah, that patch that we're burning. Yes.
Okay, so I'm going to restart the other questions. Any question? Martin, do you have a question? Anyone?
Yeah, can we go forward 1 or 2 slides if that's okay? It may be easier if I kind of where you did the kind of compared the forests and the grass. Yeah, that's great. I was just wondering what would kind of happen if you kind of with this kind of pattern you say explored moving the patch forward like every year or 2 years and see how much of an effect that would have on overall control?
Yeah, that's exactly what we did here. I was only just showing the results for a particular point in time. So we did that. We were burning every year for a period of 10 years.
No, I mean, so it's more like you kind of cycle through a series of patches that they're all next to each other. And so you're going forward. So the patch is next to the other patch. And every few years you change which patch, going around in a kind of a circle, as it were, or going through a cycle, and how the effect of those cycles has on the overall tick population, and whether or not, I'm trying to think in terms of like, you're trying to measure overall effort of burning. So instead of burning an entire huge area, you just like every year just choose to burn a little bit and then move to the next bit every other year, or every other year. It's just a general idea of kind of playing around with those sort of going round in a circle sort of patterns.
Right. That's a great idea. So more like what you're saying is that alternating the patch that we're burning.
Yeah.
We did not look at that here. That's a great idea. This is a continuing work, and thank you for that suggestion.
Okay. Thank you, Martin. And my next question is, so in this work does not account for human population, right?
No, it doesn't.
Okay. So it's the number of ticks and the infectious links versus the burning, right?
So it's the ticks and the host population, and the host population are just small mammals. So we didn't incorporate the human into this. It's not a hard thing to incorporate the humans, but in this one we did not.
Okay, good. So Idris, you have a question?
Hi everyone. So thank you very much for this great talk about such an interesting topic. So my first question is, for the eradication or control of this disease, what is the alternative solutions without harming the tick population in order to preserve it ecologically speaking? Is there any solution, for example, a genetic modification or a vaccine, a treatment for this disease? My second question about the mathematical model. When we talk about a mathematical epidemic model, we talk mainly about a basic reproduction number. So how can we differentiate between extension and persistence of an infectious disease in this model? And how can we describe it in such a spatio-temporal model?
I'm going to start with the last one. That's a good question. For the spatially inexplicit model, we did calculate the R0, but I didn't show that in this talk, so it's in the paper. For the spatially explicit, we did not calculate the R0. We were just focused on exploring the effect of fire on the spatial domain. As to how to calculate R0 for a spatial domain, Abba, are you there? Can you help me out?
For ODE system, we use a method. I think it was written by James Watmore.
For
the PDE, I don't have much experience because I work on stochastic modeling. So usually we derive it using the Lyapunov method. For the PDE, I don't have such experience with it.
Well, I thought that you're asking about the PDE. For the ODE, yes, that's the method that we use.
Yes, for the PDE, how can we derive it?
Yeah, so that's what I'm asking my mentor for help to help me out here. And I think that Ava is Ava is here. I don't know. I do not know, to be honest with you.
Professor Gomer, you're muted. Are you talking?
Okay. Can you? I don't know what happened. Okay.
So yeah, we can hear you now.
Can you hear me?
Yes, yes.
Yeah. Okay, I don't know. Sorry, I'm having a problem with my. Okay, I can't hear you.
We can hear you now.
We can hear you.
You can hear me. Okay, let's
Yes.
see. What's the problem with the volume? Okay, you can hear me. Okay, so I was just going to say that that's the simplest way to. One way is you can always convert PDEs into system of ODEs and then apply the same method, right? That's one solution you can do.
That's true.
So that you can do that, but I think there are techniques for computing reproduction number for reaction diffusion problems in epidemiology, in ecology. So the likes of Mark Lewis have done work on that, and Pauline Benden-Drisch for their forest fire. They have a technique actually for computing R0. Mark Lewis, University of Alberta, has done some of that. But there are ways, but I think the easiest way, if I were to do this, is to convert PDEs into, in principle, PDE can convert to 2 ODEs and then apply the same next generation operator method, Watmore and Benden-Drisch or Odo Dickman and Histobik. That can work. But yeah, James also has done work on, James Watmore, a good friend of ours, has done work on forest fires as well. He had a MITEX project on that a few years ago. So there are techniques to, it's the same principle, the same next generation operator method, but the speaker has done fantastic work on this and related computation of R0 for many different settings, not only for ticks, but many other. But he also asked another question, which I really like, about persistence and extinction. So that's a uniform persistence theory in mathematics, and that has also been extended to reaction diffusion. So my colleague here, Horst Thiemer at Arizona State University, and Hal Smith have done a lot of work on uniform persistence, so that we can prove that the species will persist under certain conditions. And I know the speaker also has done that as well.
Yeah.
Thank you so much, Professor Gomer. Yeah, thank you.
Thanks, Ava. That's why he's my mentor.
No, that's why we're colleagues. I'm learning from you. This is great work, actually. Great work you're doing. You know, spatial model was impulsive system, and now was this heterogeneous domain. That's just fantastic work, rich in terms of mathematical challenges, and you're doing finite element models. This is really, really amazing. I learned a lot actually from this talk. Very nice work.
Thank you so much. So do we have more questions from the audience? More questions?
No, I can ask then. Okay. You mentioned the mobility. Sorry, I can add mobility of the ticks. It's dependent on temperature. So was it a linear diffusion, and you said it's embedded in the diffusion term, right? The effect temperature.
So so right now we have not incorporated any environmental conditions into this. So it's a series of problems that we're just starting. So part of the next phase of this, that's why I was putting a plug for students, is to incorporate the environmental factors, the microclimates of the environment. And we actually have a tick team, out there collecting ticks, and they're keeping track of the microclimate of where the ticks are found. And they are collecting ticks from 2 separate sets close by, which we have captured with this particular grassland and area. So that's part of the next phase of what we want to do, to incorporate that microclimate into the model.
Excellent.
So,
very good.
So we're working on it. So it's not like we put it on the shelf, but we're working on it. Yeah.
Excellent. Great to hear.
And Dr. Agusto, correct me if I'm wrong. One of the take home here is if we cannot burn at high intensity, then we need to burn more often, right?
Right.
Okay.
Right. So part of the take home is that the duration matters.
Yeah.
And then the high intensity burn, which does a better work at reducing the tick population. But of course, as you can see from the last plots that figure that I showed there, which begs another question about where to place the control or where to even place the burn. And I like this idea that that was suggested about, having this alternating patch, burning this alternating patch. So it was something that we didn't think about when we started this work.
Okay, thank you. Oh, Martin?
Going back to that, I kind of feel I didn't kind of explain what I was trying to get at. So the idea I was thinking was, so say for a given large parcel of land, a state authority, a state health authority has only budget to burn every 6 years, the entire parcel of land. Is it better to say divide it up into sixths and burn a sixth every year? Do you get what I mean? As opposed to burn the entire lot every 6 years, kind of as a kind of comparison.
Yeah, I do understand what you mean. Yeah, we didn't think about that. So again, it was something that was started during the lockdown, and we're super excited about this project, and we're extending this work and adding more things to it. And then there's of course the math side of things, which we did not exploit in the 2 manuscript that is already out there based on the this result that I have presented today. So that math component of it is still there. It's a rich problem that we're starting to explore.
And let me ask one last question. It's a very naive question, pardon me. So I'm just curious about the type of data that you fitted to. Is it a population of ticks, or the cases
so we did not
disease, or
we did not fit
the
model to data, but rather we used the data to estimate. And then the rest of the model, we took parameter values from what's out there that other people have done. We're hoping that the data from our tick collection team, we can be able to use that in this model, in this work. And so this is the data that we use to estimate the number of ticks that are reduced as a result of fire from this published work.
So this is the number of ticks reduction per year, or
so we use the same number every time that we burn, that we implement burn from this data that we were able to find. It wasn't even easy finding this data. These two papers.
So are they used as initial conditions?
No. We used it to estimate. So let me go back to this model. Okay, so before we implement fire, we have this system of ODE for the spatially inexplicit one. So we have this system of ODE and the model parameters we got from literature. Now, when we implement fire, we have a system of differential equation that would follow this ODE before we apply fire. And now once we apply fire would reduce the population of ticks and the host by a certain proportion. And so that is captured with this system of equation. And those parameters, those reduction in the host population and the tick population, we use this data to estimate those proportion, those reduction. Yeah.
Thank you. Martin, is this a new hand or the old one?
Sorry, legacy hand.
Okay, do we have more questions? We still have like 5 minutes to go. You have more questions, contributions from everyone? Okay.
Okay, I'm gonna stop sharing.
Okay. So is Prof. Gomel talking? We can't hear you.
I was trying to echo the speaker. that this is a rich area for grad students. If there are grad students on this call, a lot of interesting problems that, so go join her lab and learn a lot about mathematical approaches to addressing these really complicated problems and in spatial ecology and persistent theory and computational reproduction number, really rich in terms of mathematical analysis as well, and numerical analysis and statistical analysis. And it's a real life problem. So I would encourage grad students to seriously consider this.
Thank you for that. Okay, so if we have no more questions, so let me give Dr. Agusto 1 minute to wrap up. Do you have anything else to say?
So anything else to say, aside from the fact that we have a beautiful campus? I'm not just focused on research. I'm also involved in capacity building in West Africa. I'm particular about West Africa because I know other great work have been done across other parts of Africa, and I don't feel we have enough as far as West Africa is concerned. So I have a sort of a mobile clinic where we've been going around a couple of countries doing some summer training for master's students and leading PhDs. So that work is ongoing, and I'm looking for funds. And so if you have suggestions as to where I can get funds, I would really appreciate that, so that the work I can keep doing the work.
Thank you so much for the great talk, and we so much appreciate your